Let's talk about our sun. It's the star at the very center of our solar system, and it's incredibly important. In fact, without the sun, there would be no life on Earth at all. Think of it as a gigantic, fiery engine, constantly burning and sending out light and heat in every direction. This energy travels all the way to our planet, warming our seas, stirring our atmosphere, and giving energy to the growing green plants that provide the food and oxygen we need to survive. It's a massive ball of super-hot gas, mostly hydrogen, helium, held together by its own immense gravity. It's so big that you could fit 1 million Earths inside it. Consider that for a moment. Now, the sun isn't just a calm, steady ball of light. It's a very active, dynamic place. Its surface is a churning cauldron of plasma. That's a special state of matter, a super-hot gas where electrons have been stripped from their atoms. This activity creates powerful magnetic fields, which are like invisible lines of force that twist, stretch, and sometimes snap. These magnetic fields get tangled up like a bunch of rubber bands, storing up huge amounts of energy. When they get too tangled, they can suddenly release that energy in a spectacular burst, which is the starting point for all sorts of interesting space weather that can affect us here on Earth. This constant activity on the sun is what we call the solar cycle. It's a pattern that repeats roughly every 11 years. During a period called the solar minimum, the sun is relatively calm and has very few sunspots. Sunspots are cooler, darker spots on its surface caused by intense magnetic activity. But then, it slowly ramps up to a solar maximum, where its surface becomes covered in sunspots and it's much more active. During this peak activity, the sun is more likely to fling out massive amounts of energy and particles into space. So what exactly is a solar storm? Imagine the sun has a really big sneeze. A solar storm is a massive burst of energy and particles. There are a couple of types. One is a solar flare, an intense flash of light and radiation, like a giant flashbulb on the sun. The other is a coronal mass ejection, a CME. A CME is when the sun throws a huge chunk of its atmosphere, a giant cloud of plasma and magnetic fields, out into space. Think of a CME like a cannonball of super hot gas. It can contain billions of tons of material and travels at incredible speeds, sometimes millions of miles per hour, fast enough to reach Earth in a day or two. CMEs launch when tangled magnetic field lines snap and reconnect, releasing stored energy in a massive explosion. A Cannibal CME happens when a faster, stronger solar storm overtakes and essentially eats an earlier, slower one. It's a cosmic pileup in space. Imagine the sun releases a CME and it starts traveling through space at a certain speed. Then, a little while later, maybe a day or so, the sun unleashes another, much faster CME in the exact same direction. The second storm races through space and catches up. They collide and merge into one giant superstorm. The faster CME plows into the back of the slower one, compressing the plasma and amplifying magnetic fields. The combined storm front becomes far more complex and powerful. Result: the Cannibal storm is bigger, denser, and has a more jumbled, potent magnetic field. The first, slower CME acts like a snowplow, clearing a path. That lets the second CME travel with less resistance and keep speed until impact. When merged, the particle cloud is larger and its magnetic structure becomes tangled and intense. That tangled field is what interacts with Earth's magnetic shield when the storm arrives. Scientists watch these events closely because they can cause the most powerful geomagnetic storms on Earth. A Cannibal CME packs a much bigger punch, so forecasters watching two CMEs along the same path pay very close attention. So how does a Cannibal solar storm create those beautiful, dazzling lights in the sky we call the auroras? Well, it all has to do with Earth's magnetic field, our planet's invisible force field. This field, called the magnetosphere, protects us from most of the charged particles the sun sends our way. It acts like a shield, deflecting the solar wind around our planet. However, when a powerful storm, especially a potent Cannibal CME, hits our magnetosphere, it can cause a major disturbance. The storm's magnetic field presses against and connects with Earth's field, transferring a huge amount of energy into our system. This massive injection of energy from the solar storm makes our magnetosphere shake and wobble. It channels some of the supercharged particles from the storm along Earth's magnetic field lines, directing them down toward the north magnetic pole and toward the south magnetic pole. These particles, mostly electrons and protons, are traveling at incredible speeds. As they get closer to Earth, they slam into the gases in our upper atmosphere, gases like oxygen and nitrogen. It's kind of like a cosmic scale game of billiards, with solar particles being the cue balls and atmospheric gas atoms being the targets. When these high-energy particles from the sun collide with the atoms and molecules in our atmosphere, they transfer their energy. This excites the atmospheric atoms, putting them into a higher energy state. But atoms don't like to stay excited for long. They quickly release that extra energy in the form of tiny flashes of light. When billions and billions of these atoms are all releasing light at the same time, we see it as the beautiful dancing curtains of the aurora. The different colors are created by different gases at different altitudes. Green, the most common color, comes from oxygen about 60 to 150 miles up. Red auroras are produced by oxygen at even higher altitudes. A cannibal storm, being more powerful, can dump a much larger amount of energy and particles into our atmosphere. This means the resulting auroras can be incredibly bright, widespread, and dynamic. Instead of a faint glow on the horizon, you might see vibrant curtains of green, pink, and red light rippling across the entire sky. Because the storm is so strong, it pushes the auroral zone, the area where auroras are normally seen, to lower latitudes. This is why, during a major solar storm, people in places like the northern United States or Central Europe might get the rare and breathtaking chance to see the northern lights, far from their usual Arctic home. While cannibal solar storms produce amazing auroras, they can also cause some serious problems for our technology-dependent world. The same energy that creates the beautiful lights can wreak havoc on our infrastructure. The powerful geomagnetic storm can induce electrical currents in the ground. These currents can flow into long conductors like power lines and overload the electrical grid, potentially causing widespread blackouts. Our satellites are also at risk. The energized particles can damage the sensitive electronics on board the thousands of satellites we rely on for communication, GPS navigation, weather forecasting. That's why understanding and predicting these storms, including the powerful Cannibal CMEs, is so incredibly important. Astronauts in space, particularly those on the International Space Station, are also at increased risk from the higher levels of radiation and may need to take shelter in more heavily shielded parts of the station. The storm can even cause the Earth's upper atmosphere to heat up and expand, increasing the drag on satellites in low Earth orbit and causing their orbits to decay faster than expected, which requires them to be reboosted. The effects can even reach us on the ground and in the air. High-frequency radio communications, used by airlines to communicate on long-haul flights over polar regions, can be completely blacked out. GPS signals can become scrambled and unreliable, which could affect everything from shipping, farming, to the navigation app on your phone. These are all reasons why space weather is not just an academic curiosity. It's a matter of practical importance for our safety, economy, and daily lives. We are more connected and therefore more vulnerable than ever before. By studying the sun and monitoring its activity, scientists can provide us with advance warnings. These warnings give power grid operators time to protect their systems, allow satellite operators to put their spacecraft into a safe mode, and help airlines reroute flights. As our society becomes even more reliant on technology, our need to understand the weather in space will only grow. So the next time you see a beautiful picture of an aurora, remember the powerful science behind it. A cosmic dance that connects us all to our amazing star, the sun.